Let's take a closer look at atoms. Atoms are the building blocks that make up everything, all stuff, everywhere. Here I've got some drawings. This is table salt, a solid. Here's water, a liquid. And finally, oxygen gas. And what we're looking at here is what we'd see if we could take these three things and zoom in zillions and zillions and zillions of times. And if we could look at these closely enough, we'd be able to see the atoms, these little building blocks that make everything up. Now, atoms aren't really little colored circles, but it's a good way to think about them, and it's the way we'll usually draw them when we're learning about this stuff. Atoms are super tiny. They are so tiny, it can be really hard to wrap your head around how tiny they are. Here is something that might help you think about this. Take a piece of paper. Look at how wide it is here, all right? This is so incredibly thin. Now, atoms are so small that it would take 1 million atoms lined up next to each other in a row to be as thick as this tiny width of paper. That's how small atoms are. Now, what I want to do now is look even closer at an atom. Let's take one of these atoms here and zoom in even more so we can see what's inside of it. Here's a magnified view of one atom. It's not a perfect representation of exactly what an atom would look like, but it's close enough for right now. And check this out. The atom itself is made up of even smaller things. Right, so that we said atoms are like the building block for all of stuff. But then if you look at an atom, it has even smaller building blocks that make it up. So in the center of the atom is something called the nucleus. And the nucleus is made up of two tiny particles. There are protons, which I've drawn as red circles here, and then there are neutrons, which I've drawn as blue circles. Nucleus is here in the middle of the atom. And then on the outside of the atom, there are these little black circles that I'm using to represent electrons. The electrons, you'll see, are connected to these sort of oval paths, and I've drawn these in to show that the electrons are constantly moving. They're flying around the outside of the atom at an incredibly high speed, whereas the nucleus stays solid here right in the middle of the atom. Now, electric charge is very important when we're talking about atoms for a number of reasons. Protons have a positive charge. A proton has a charge of 1+. Electrons, on the other hand, have a negative charge. One electron has a charge of 1-. Now, neutrons, they don't have an electric charge at all. They have a charge of 0. And neutral is a word that we use to refer to something that doesn't have a charge. So neutrons sounds a lot like neutral. Now, positive and negative charges attract. Remember that? Opposite charges attract. And that has important consequences for how this atom works. We said that these electrons are flying around the outside of the atom. They're moving really fast. So why don't they just fly out into space? Well, the reason why is because the negatively charged electrons are attracted to the positively charged protons. So the protons kind of pull the electrons in. They keep them from just flying away. But the electrons are moving around so fast that they're not able to actually pull in here and actually touch the protons. So that's why they keep staying on the outside and don't just crash in here and all touch the protons. Now, sometimes people ask, well, neutrons don't have a charge. Why are they important at all? Here's a diagram of an atom. It's not perfectly accurate, but for what we need right now, it's going to do just fine. So in this lesson, we're going to look at characteristics that we can use to describe atoms like this one. You know, if somebody asked you to describe a person, chances are you'd use characteristics like the color of their hair, the color of their eyes, what their height is, and so forth. Just like that, there are characteristics we can use to describe atoms. The first of these characteristics, and maybe the most important, is the atomic number. The atomic number is often abbreviated by a capital letter Z. And what the atomic number is it's the number of protons in the nucleus of an atom. In my diagram here, I'm using these red circles to represent protons. So I have 1, 2, 3 protons in this atom. So the atomic number is going to be 3 for this atom here. Atomic number is particularly important because the number of protons in an atom tell us what kind of an atom it is. And by that I mean, is it a carbon atom? Is it an oxygen atom? Is it a sodium atom? We're going to talk more about that in the video on isotopes, so you don't have to worry about it for right now. The next important characteristic that we can use when describing atoms is the mass number, often abbreviated by an uppercase A here. Mass number is the number of protons plus the number of neutrons in the nucleus of an atom. People always get confused by mass number. Here's why. Atomic number is the number of protons. So everybody always wants mass number to be the number of neutrons, but it's not. It's the number of protons and neutrons. In fact, there's not really a name for the number of neutrons, just the number of neutrons in an atom. We just don't use it that often. So anyway, for mass number, we want to count all of these together. 1, 2, 3, 4, 5, 6, 7. The mass number of our atom here is going to be 7. Now finally, the third characteristic we're going to talk about here is probably the most complex, and that's called net charge. I don't have a good way to define net charge. I don't have a good definition. So what I'm going to say here is it's how protons and electrons balance each other out. Let's talk a little bit more about this. So net charge is about how protons and electrons balance each other out. So protons, as you know, have a positive charge, and electrons have a negative charge. So that means that if we have the same number of protons and electrons in an atom, like I have right here, 3 protons and 3 electrons. I'm not drawing the neutrons here because we're not worried about them. Here we have the same number of protons and electrons. They're going to balance each other out. This 3 minus is going to balance out the 3 positive. So we're going to end up with an atom that has a net charge of 0 because these two things balance out, and we can call this atom neutral, which means that it has no net charge. Now, what would happen in an atom where we have 4 protons and 3 electrons? We don't have the same number of electrons and protons anymore, so they can't totally balance each other out. Instead, we have more protons than electrons, so that we're going to have a net charge that's positive because there's going to be some of this positive charge in the protons that can't be balanced out by the electrons. In this case, we have 1 more proton than electron. So this is going to give us a net charge of +1. Since our atom has a net charge, we give it a special name. We call it an ion. An ion is any atom that has a net charge. Neutral is what you call it if you don't have a charge. Ion is what you call it if you have any charge. Okay, this is where we have 1 more proton than electron. What about this case here? What if we had 5 protons and 3 electrons? In this case, the charges don't balance out either, but now I have 2 more protons than electrons. I've got 2 more protons that aren't getting balanced out by these electrons. So that means that I'm going to have a net charge of 2+ for these 2 protons. And again, this is going to be an ion because it's got a charge. Now the opposite can happen as well. Here is an example where an atom has 4 electrons and 3 protons. So now it's got more electrons and protons. These 3 protons can only balance out 3 of the electrons, so I have 1 more electron that's not getting balanced out. That means that this total charge is going to be -1. That's a charge of this 1 more electron that I have in the proton. Here's an atom. What's the atomic number, the mass number, and net charge of this atom? So atomic number is the number of protons. In this diagram, these little red circles are representing protons here in the nucleus. So I've got 1, 2, 3, 4, 5, which means that my atomic number is 5. That was easy enough. Mass number is the number of protons plus the number of neutrons, which are these things in blue. So the mass number is 1, 2, 3, 4, 5, 6, 7, 8 protons plus neutrons. So mass number is 8. Sometimes people think you have to have the same number of protons and neutrons in the nucleus of an atom. Definitely not true. They can differ quite a bit. The net charge is how the protons and electrons balance each other out. So, electrons are represented by these things here flying around the outside of the atom. 1, 2, 3, 4. 4 electrons, E minus is a way that we can abbreviate electron, and 1, 2, 3, 4, 5, P plus, protons. So, the protons and electrons don't quite balance out. There is one more proton than electron. So that one extra proton is going to give me a net charge of 1 plus, because each proton has a positive charge. I have one extra proton, net charge of 1 plus. This is kind of a basic problem. Now we'll move on to stuff that's a little trickier. So here we've got an atom with this atomic number, this mass number, and net charge. From this information, we need to figure out the protons, neutrons, and electrons that are in this atom. Protons, that is going to be easy because protons, number of protons, is the same thing as atomic number, so that's going to be 7. Now what about neutrons? Mass number is protons plus neutrons. So this 15 here is protons and neutrons together. I already know how many protons there are, so I can do protons plus neutrons, the mass number, minus the number of protons equals 8, the number of neutrons. Net charge here is plus 2. If I have a positive net charge with a certain number, that's telling me how many more protons I have than electrons. So in this case, net charge of plus 2, there are 2 more protons than electrons. Since I have 7 protons, that means that I have to have 5 electrons for me to get a 2 plus charge. What are isotopes? Isotope is a word that gets thrown around in chemistry a lot. So what are they? Really quickly, isotopes are different versions of an element, or different versions of a certain kind of atom. This can be a tricky concept though, and a lot of people get confused by isotopes. So I want to describe them by starting out with an analogy to cars, okay? I want to talk to you about the made-up car called the Lamona, the epitome of luxury, and it's known for its very distinctive styling. As you'll see, the Lamona looks like a lemon. Now the Lamona comes in 3 different models. There's the Lamona G, the Lamona GX, and the Lamona GXL. They're all different colors, as you can see, but each of these models also has unique features. One has a radio and leather seats. The GX here has chrome wheels and a CD player. It's blue. The red GXL has massaging seats, platinum spinner wheels, and everything. But here's the point. They are all Lamonas. They're all Lamonas because they all have this distinctive styling. They look like a lemon, and that's what makes a car a Lamona, okay? So it doesn't matter what color it is, and it doesn't matter the various options that you get in these models, the GX or the GXL. What matters is that they all have this particular shape. That's what makes a Lamona a Lamona. So we have these 3 different models. I want to use this analogy now to talk about the same thing but with atoms. I want to now introduce you to 3 models of carbon, just the way there are 3 models of the Lamona. Okay? Here are the drawings of each one of them, and what we're particularly concerned about is the nucleus. I'm using these red dots to symbolize protons, and I'm using the blue dots to symbolize neutrons. The swirly circles are supposed to represent electrons that are buzzing around the nucleus, but we don't really want to worry about that too much right now. Anyway, these 3 models of carbon are carbon-12, carbon-13, and carbon-14. Let's look at the options in them. Like we did with the Lamona, let's look at how each one of these different types of carbon differs. Okay? So, if we count the number of protons in carbon-12, we'll see that it has 6 protons, and if I count all the blue spots here, I have 6 neutrons. Okay? Carbon-13, 1, 2, 3, 4, 5, 6. Red spots, 6 protons. In this one, I have 7 neutrons, and in carbon-14 down here, I have 6 protons, and I have 8 neutrons. So what do we have in common here? All the different models of the Lamona, even though there are things that they differed about, all have the same distinctive lemon-like shape. So for carbon, what they all have in common is they have 6 protons. 6 protons in the nucleus. And that's what makes a carbon atom, okay? So it turns out that it doesn't matter how many neutrons it has. 6 neutrons, 7 neutrons, 8 neutrons, no big deal. It's just like painting the lemon different colors or adding a radio or a CD player. The neutrons, it doesn't matter. It doesn't change the fact that each one of these are a carbon atom. That's because carbon is defined by the fact that it has 6 protons in its nucleus. If you look it up on the periodic table, you'll see something that looks like this, and the number up here is the atomic number, 6, which means that if an atom has 6 protons, it's carbon. Okay? So that's what these all are. They are all isotopes of carbon. They're different versions of carbon or different models of carbon with the same number of protons and different number of neutrons. So look at how I wrote this. I've got carbon 12, carbon 13, carbon 14 up here. I want to take a minute and talk about the numbers. So the number of protons in the nucleus, we call that the atomic number. You may already know that. And then carbon 12, this 12 that I've written here, refers to a different number, and we call that the mass number. The mass number, as you'll see, is the number of protons plus the number of neutrons. So this is carbon 12. 6 plus 7 protons and neutrons is 13 here. 6 plus 8 is carbon 14 here. So that's how we distinguish between these different isotopes, different types of carbon. There's another way that we sometimes indicate these different isotopes of an atom instead of doing 12 and 13 or 14, and that's by using something called isotope notation. Let me show you how we do that. The way we write carbon 12 or 13 or 14 in isotope notation is we start out with a chemical symbol. If you don't already know that, you can find it on the periodic table. So here it is. It's a big uppercase C. So I start with my C for carbon. And then on the lower corner here, I write the atomic number. So that's going to be 6. And then up top, I write the mass number, which is 12. So this is carbon 12 written in isotope notation. Carbon 13 is going to be 6 again, because all carbon has 6 protons in its nucleus. But then the 13 up here. And finally, carbon 14, written in isotope notation, is C614. So that's how we can write all these isotopes of carbon in isotope notation. And of course you can also write it as just the element name with a dash and then the number. So given just these 2 pieces of information, we've got to figure out everything else. This is kind of like a puzzle or a logic game, kind of like Sudoku. We'll go step by step so you can see how to do this. Let's start here. The chemical symbol is Na. So we'll look up Na on the periodic table, and we'll find out that that is a symbol for sodium. So now for the isotope name, we know that this is going to be sodium. Now that's only the first part. The isotope name tells us what element it is, and then it has the mass number after it, number of protons plus the number of neutrons. The mass number has already been given to us, so we know that the isotope name is going to be sodium from Na, and then 22 from the mass number. Now that we know that Na is sodium, we can fill in the atomic number and the number of protons. Because when we look this up on the periodic table, Na sodium has 11 at the top. This number up here is the atomic number of protons. So 11 for the atomic number, 11 for the number of protons. Now, for the number of neutrons, the mass number here is the number of protons plus the number of neutrons. So if we want to find out just the number of neutrons, we can do protons and neutrons minus protons equals 11 neutrons. That's how many neutrons we have. Now finally for electrons, let's look up here at our symbol. Okay? It's written Na1+, because there's just one plus sign there. So it's 1+. Okay? This is the net charge. The net charge tells us how protons and electrons balance out. So if it's 1+, that means there is one more proton than electron. So 11 protons, which means that we have 10 electrons will give this atom a 1 plus charge. So based on just these two pieces of information, we were able to figure everything else out. Here we know protons, neutrons, and electrons. Let's start with protons. 44 here. We can look up on the periodic table and find out which element has an atomic number of 44. Okay? If you got 44, you're ruthenium. So I can put that up here as the isotope name, ruthenium. But I'm still going to have to come back and deal with a mass number that we put after here in the isotope name. Atomic number, I can take care of that right away. It's 44, the number of protons. Don't even have to look it up on the periodic table to fill this in. Let's move ahead now to mass number. Mass number is protons plus neutrons. So I'll do 44 plus 56. And that's going to give me 100 total for the mass number. Now I know the mass number, so I can put it here at the end of the isotope name, ruthenium 100, and I'm all set with this. The only thing that I have left now is the chemical symbol with a net charge. Let's go back to the periodic table. Here it is to find out what the chemical symbol is. The chemical symbol is right here. It is Ru. And now for the net charge that we'll put up here, it's protons and electrons. So there are 44 protons and 40 electrons. That means there are 4 more protons than electrons. So there's going to be a net charge of 4 plus. Ru 4 plus is going to finish this off